Hi, so in the second lecture, I'm going to discuss some anonymous results for self-shrinkers. So, as we talked about in the previous lecture, there's a patchwork of examples of self-shrinkers constructed by various means, the desingularization of the sphere and the plane, these min-max instructions, blah, blah, blah. And kind of what I was trying to convey was that the space of self-shrinkers is still generally pretty poorly understood outside of some curvature convexity assumptions like mean convexity or entropy assumptions. But it turns out that we can still say something about that are embedded, at least for self-shrinking surfaces in R3. In today's talk, I want to discuss the following result with Shangwen Wan. It says that a closed self-shrinker of genus G is isotopic to the standardly embedded genus G surface in R3. And the standardly embedded genus G surface in R3, if you think about a donut has being standardly embedded genus 1 surface, then a genus G surface can be gotten by lining them up and then connecting adjacent donuts, if you will, by just straight cylinders in the obvious manner. So no donuts link with each other or anything else like that. Okay, I think that should be reasonably clear. And as a corollary, in particular, just thinking about the genus 1 case, it says that a self-shrinking torus can't be the tubular neighborhood of a knotted S1. So that's why you can call these types of things unknotedness results, because it really comes down to an unknotedness of the central curve, so to speak, in the genus in the torus case. So in particular, because of course the angular torus is unknotted, you can think of this as the uniqueness for the angular torus up to isotopy. Any other self-shrinking torus in R3 is at least isotopic to the angular torus. Speaking of which, I wonder if you could phrase something along these same types of lines for immersed. I'm not sure if the question can even be made to make sense, but I'm just throwing it out there. So, prior work along these lines, the first result of this kind, at least to my knowledge, is that minimal surfaces in S3 with Ricci positive or Ricci positive metric or topologically standard. So, for example, in the round metric, due to Blaine Lawson. In fact, I think this paper is where he proposed the Lawson conjecture. And later on, Bill Meeks and others, including Froman and Yao, particularly prominent for minimal surfaces in R3, they proved unknotedness results for minimal surfaces in other contexts. In other words, not just in S3, but let's say in the torus, 3 torus or whatever. So for instance, self-shrinkers in R3 are topologically standard in that you can think of taking, let's say, k planes corresponding to k ends, stacking them, if you will, with straight cylinders in between adjacent planes, and then attaching some genus G surface at the end. That's standardly embedded. Key and Lawson's argument are the following 2 facts. The first fact, due to Frankl, is that any 2 minimal surfaces in a Ricci positive manifold must intersect. The second fact, a deep result from 3-manifold topology, is that any 2 genus G Haggard splittings of S3 are ambiently isotopic. So, of course, we're going to show that minimal surfaces are Haggard splittings and use this theorem. So how does Frankl's theorem go? Well, it's a variation argument. You suppose that there are 2 minimal surfaces in such a manifold of Ricci positive metric that don't intersect, then you can consider a curve between them that minimizes distance. And then you take the second variation of the length of the curve. So since it's length minimizing, this side here should be positive. But on the other hand, this will be 0. This will be 0. Of course, note that you can generalize this to some mean convexity condition. Anyway, this will be positive. This is 0, 0, strictly negative. Because Ricci G is strictly positive. So that gives a contradiction. Okay. Right. And there's also a Frankl property for self-shrinker for the self-shrinker metric, for the Gaussian metric. So you can see this pretty quickly. For smooth shrinkers, at least one is compact by the following argument, just using the comparison principle. As before, suppose that there are two disjoint self-shrinkers. Let's call them sigma 1 and sigma 2. You can suppose sigma 1 is compact. And suppose that the distance is bounded below by delta. Well, by the comparison principle, their distance must be non-decreasing. All right, the comparison principle being the thing that we use to show that compact hypersurfaces must develop a singularity in finite time by enclosing it around here. It was that principle. So the distance has to be non-decreasing, but on the other hand, the flows both have a singularity at the origin after 1 second. After 1 second of the flow, and so that means that there actually must be points coming together as we approach t equals 1, and this gives a contradiction. So this has been proven in wider generality by Chodas, Choi, Mantulius, and Scholze in their generic mean curvature flow paper. They can allow for non-compact self-shrinkers and more. And there's also an elliptic argument for non-compact self-shrinkers that is by Impera, Pegola, and Ramoldi. So this includes a separation and infinity assumption. It's not too strong though at all. And also it uses polynomial volume growth. Now polynomial volume growth for self-shrinkers, I'm talking about minimal surfaces in the self-shrinker metric in Rn, are polynomial volume growth if they're proper by work of Dean and Shin, although this will come up below, actually. So with this in hand, you should be able to prove some sort of a oddness theorem for your self-shrinker metric, of course, and this makes sense, again, because the self-shrinker metric is like the Ricci positive metrics. And there's also a Frankl property for non-flat classical minimal surfaces. If we proved an oddness theorems, there shouldn't be a surprise that there'd be such a statement. More or less by a moving plane argument. So you suppose that there's two disjoint non-flat, say, classical minimal surfaces, and you can minimize in between them, and you find a plane. Yeah, I'm being a little rough and maybe not super accurate, but this is basically the idea. And then you can shift the plane up, and you get a contradiction to maximum principle. It's like the half space property for minimal surfaces in R3. Right, so of course they have to be non-flat. The planes, right, these are flat, and you can foliate R3 of planes, so, and these are all disjoint, so that's where the non-flatness comes in. Right, so kind of relatedly, and again along the theme that the self-shrinkers are like minimal surface and Ricci positive, there's no stable self-shrinkers, at least of polynomial volume growth. So to see that, well, let's look at the Jacobi operator for shrinkers, the second variation of area, that is, in the Gaussian metric. And you see that you get this 1/2 term, this extra 1/2 term. So this tells you, at least in the compact case, but it also works in the non-compact case with polynomial volume growth, that you should be able to just plug in 1 here to see that the index has to be non-zero. Now, you use polynomial volume growth because you have to work in the appropriate O2 spaces, so it's kind of a technical thing for the spectral theory, I'll say. This can be used, at least I will use it below, as a stand-in of the Frankl property. I'll discuss that in a second. Also, I just want to point out that like in Ricci positive 3 manifolds, you can use this effect to prove a compactness theorem for self-shrinkers in our... So what's a Haggard splitting? A Haggard splitting is a decomposition of a 3 manifold into 2 handle bodies, and the 2 handle bodies share a common boundary, and that boundary is the Haggard splitting. So this popped up. I'm pretty sure the history behind it is, well, what's a natural way to construct 3 manifolds? Well, we have handle bodies. You can think of these as like kettlebells, if you will. In R3, there's a 3 manifold with boundary. And how could you construct a 3 manifold without boundary? Let's try to glue another kettlebell, if you will, along their common boundary. And you would get something that's boundaryless. And also this way you can apply techniques from studying surfaces to studying the whole manifold. By Moises' theorem, every 3 manifold is triangulizable and hence emits many Haggard splittings. And I'll just say that they're an important study. They're an important object of studying 3 manifold topology. I'm not a 3 manifold topologist, although I do use some of their facts. So maybe I'll just leave it at that. So Waldhausen's theorem, in particular, is that all Haggard splittings of the same genus of S3 are isotopic. There's a number of generalizations. For example, a splitting of a ball of one boundary component, in the appropriate sense, it will also, those will also all be isotopic by Waldhausen. But there's no statements which allow for multiple boundary components. So there's examples due to Peter Hall using minimal surface theory, actually, in the bridge principle, to construct some minimal surfaces that are knotted tori with 2 boundary components in the 3 ball. Right. So how to show a surface of the Haggard splitting? Let's just talk about in S3, or I think of S3 as being R3 plus a point at infinity for the sequel. And if you just think about, say, genus 2 surface, well, it will split S3 into 2 parts, and I'll call one NX and one N interior. So the exterior, I would say, is the part containing infinity, and the interior is the bounded region. Now, generally speaking, there's not really a distinction between the two, at least in the non-compact case, but we can make a distinction when the surface is compact. Of course, one of these is going to be bounded. Right. And we want to show that sigma is going to be a Haggard splitting of S3. And then we can use Waldhausen's theorem. So Lawson observed that the surface sigma in S3 is a Haggard splitting exactly when the induced map on fundamental groups is surjective. When you include sigma into either this NX or NIT domains of boundary, that the map on pi 1 is actually surjective. So there's not any extra loops, so to speak. And it turns out that you can actually boil this down by some covering space argument to say that you need that in the universal covers of this region of boundary and this region of boundary, that the boundaries have to be connected. And the idea then would be to use this to somehow force a contradiction. So in particular, why is this a good reformulation for us? Well, we have Frankl properties, right? So these boundaries here, because sigma is minimal and it's metric, these boundaries, even when you lift everything, you're also going to lift the metric, right? You'll still be minimal. And then because you're talking about two, so supposing that there are actually 2 boundary components or more for either of these, you would then hope to get a contradiction using the Frankl property. And this is basically what Lawson does in his paper, but things are a little bit more complicated for self-shrinkers. So the area growth of the boundaries could conceivably be greater than polynomial. And so that rules out the use of the Frankl property. Of course, these boundaries are going to be non-compact. And so, unless if you're a sphere. So that rules out the argument by the Italian group, and the parabolic proof that we talked about above really is only for shrinkers in Rn, because you're talking about the shrinker collapsing down to a specified point. But roughly speaking, the origin has many lifts in the universal cover. So the scheme is suppose you still want to use that you still want to do a proof by contradiction. Suppose that there's many boundary components of either this, many boundary components of either the universal cover of an exterior or the universal cover of an interior, but somehow do some of the work downstairs, some of the work in the base instead of the universal cover, because that's where our Frankl properties live. Right. So the scheme in our original paper is to do a minimization argument in the universal cover and then project it down and then say, well, we get a contradiction by Frankl. So you would consider, so suppose that there's two boundary components. Let's suppose that this is the universal cover of an interior, say, or an exterior. And you exhaust one of the boundary components with domains, and then you solve plateau problems along the boundary of those domains. I call them pi I here. And because these are disjoint, you can connect them with a curve gamma, and this sigma I here, this is the solution to plateau problem along this boundary, the boundary of this guy here. This is going to have intersection number odd with gamma. And so then when you pass the limit, you'll get something that is you'll get a non-trivial limit, and it will be stable. Now, stability right away doesn't imply a contradiction for self-shrinkers, because this is in the universal cover, and you don't know that what you get actually isn't going to be let's say exponential volume growth or whatever. So you don't necessarily know too much about it, but then the idea we had was to project it down and then use the comparison principle argument that I talked about above. Now, this had some issues, actually. Some subtle issues. So the limit you get, it's not necessarily clear that it's equivariant, for instance. So how do you know that you're going to project it down and actually get embedded self-shrinker, even something that's proper, right? You could project it down to something that's very, very complicated. So to get around these issues, though, you can use the flow method. And maybe I'll just briefly describe this. This is something that I do in my later papers on the non-compact self-shrinkers. This is recent work on the archive. So what I propose there is to consider outward flow or an inward flow, depending on which domain you're considering. You run the mean convex, mean curvature flow, shrinker, mean convex, mean curvature flow, and you look at the lift of this flow, and using the same type of intersection argument, you should get something that's non-empty. But then, because we're taking the lift of something from the base, the limit is still going to be proper, embedded, whatever. And so these issues that we had from projecting down a minimal surface in the lift aren't going to be an issue. The limit, by the way, so this will be a stable self-shrinker because the flow is mean convex by deep work of Brian White on mean convex, mean curvature flows. So I will say that the general idea in our paper still is basically seems to work, at least for the compact case, because you could do a mean convex outward perturbation so that these lifts aren't minimal, so you don't have to worry about when you solve this sigma I to be equal to one of these boundary components. That is also another issue I guess I forgot to say. And So you'll get some sigma I. Again, its projection down will still be non-proper, but at least it'll be disjoint from the original self-shrinker. And it seems that in this case, because the first self-shrinker is compact, that you should still be able to use the maximum principle to get a contradiction. So hence in R3 union infinity, so this is S3 again, any compact self-shrinker genus G is ambiently isotopic to the standard genus G surface. And by moving the isotopy away from infinity, you can make sure that the isotopy is completely in the R3 part, so to speak. And so then that gets the statement that any genus G self-shrinker in R3 is isotopic to a standardly embedded genus G surface. Right. Thank you for your attention, and thank you, Hoju, again for setting up this conference. I think it's really great that everyone, still tries to do math during the pandemic, like I've said.